Now I request Dr. T. Michael Joseph Stalin, Professor of Mechanical Engineering Department and Additional Controller of Examination, the Additional Deemed University, to introduce our guest speaker to the gathering. Sir, please, sir.
So, good evening to everyone. So, I am Dr. P. Michael Joseph Stalin in the Department of Mechanical Engineering and Additional Control of Examiner at Adhisankara Deemed to be University, Gudur, Andhra Pradesh. It's my privilege to introduce our esteemed resource person for this session, my friend and colleague, Dr. S. Vijayan, presently working as a professor in the Department of Mechanical Engineering at Coimbatore Institute of Engineering Technology, Coimbatore, India. He received his bachelor, master, and PhD degree from Anna University in 2006, 2011, and 2018, respectively. Driven by a deep passion for research, he pursued postdoctoral studies at the National Institute of Technology, Tiruchirappalli, specialization in thermal energy storage from December 2019 to May 2022. With over 15 years of combined experience in industry, academia, and research, he has made significant contribution in the field of energy utilization and emission control. His research has been pivotal in advanced technologies that improve energy efficiency and reduce environmental impact. As a co-principal investigator, he the Department of Science and Technology, India, funded research project titled Development of Solar Evacuated Tube Collector with inserted bubbles with direct air heating in industrial application with a total project cost of 1.62 crores. Additionally, he was awarded served under securing a grant of rupees 23.76 lakhs for 3 years. He has authored more than 35 peer-reviewed international journal publications, 15 international and national conference papers, and 10 book chapters for Springer Nature, CRC Press, elsewhere, and others, contributing extensively to the body of knowledge in this field. His editorial contribution include the book Solar Thermal Conversion Technologies for Industrial Process Heating, published by CRC Press in 2023, and a book titled Efficient Energy Utilization and Emission Reduction Strategies in Plant Operation, first edition, also published by CRC Press in February 2025. His innovative work has been recognized with 5 granted patents, comprising 2 international and 3 national patents. In addition to his research and academic endeavor, he served as an associate editor for the Journal of Advanced Material Science and a reviewer for various reputed journals. Apart from his academic achievement, he is serving as a co-founder and technical head at Cine Unicorn Solar Technologies Private Limited, which is focusing on solar thermal application. His currently research interests focus on solar thermal conversion system, thermal energy storage for low and medium temperature application, and advanced heat transfer techniques. We are privileged to have him with us today. Please join me in extending a warm welcome to Professor Dr. S. Vijayan to share his insight with us. On behalf of the organizer and all participants, I extend a very warm welcome to you, sir. With this word, now I hand over the session to our esteemed resource person, Professor Dr. S. Vijayan.
Okay, thank you so much for your nice introduction, sir. Okay, sir. So, are you able to see my screen, sir?
Yes, sir.
Good evening to everyone. So first, I would like to express my sincere thanks to the coordinators for giving me this opportunity. So, hope I am the last person in this FDP. Today, I'm going to deliver a speech on this progress in energy storage for industrial process heating applications. So I think Michael has given a detailed introduction about me, so I don't want to repeat this again. So um, during my academic thing, so I've carried out many research activities. So some of the things have been listed here. The Solar Energy Research Center, where they have established almost all kind of a solar thermal application, and they have tested it. So and we have an indoor facility to test the solar thermal system, solar thermal simulator. And again, this DFC funded project, a solar process heating application. So where they are able to produce a temperature which is ranging from 70 degree to 120 degrees Celsius, which is optimum, highly suitable for an industrial process heating. And we have already installed a system at a leather factory. This is the system which is installed at our institute. So the overview of this presentation. So today I'm going to talk about this general introduction about the global CO2 emissions, industrial energy consumption pattern, and again the process temperature ranges. Then the adaptability of this solar thermal energy for the industrial process heating applications. Then the need of the thermal energy storage and some of the commercial thermal energy storage systems. So a question may arise here, right? So why do you want to move, or why do you want to focus on this industrial process heating? So before moving on this, we need to know about the CO2 emission statistics. So here you could see that the CO2 emission, which has been a very higher rate, and that causes many issues in the current scenario. So all the countries are focusing on reducing this carbon emission. So here you can see that during the pandemic situation, that is during the COVID situation, there is a steep drop in the carbon dioxide emission, and again it's been reached its maximum capacity now. So during the year of 2022, it's about 36.1 gigatons. So further, if you want to go in detail, so the industry which emits about 24% of CO2, and other than this, so next thing is of electricity production, it's about 22%, and for the agriculture sector, so it's about a 22%. So here the question arises, so in what way we used to get a CO2 from an agriculture sector? So the almost cultivating lands like rice or other paddy fields. So where we are storing a water for longer duration, that leads to formation of the biomass that emits a huge amount of the methane and other carbon dioxide. And apart from this, the animals, the cattle that we use, so they are also the waste which produces like methane. So thereby the CO2 has been emitted a lot. By the way, it contributes a major portion of the CO2. Apart from this, the transport and other sectors, they are also be contributing. So slightly it's lesser than these three sectors. So a question may arise here. So why do you want to focus on this industrial heating? So here the thing is that for heating or the cooling purpose, we are taking about more than 50% of the global energy. So out of which the 30% has been only taken up by this industrial process heating. So in this 30%, the most of the energy, especially for the heating applications, we are taking 90% of this heating load is been purely made with the fossil fuels that are natural gas, oil, and the coal, and which results in the around 24% of the global emissions. So because of that reason, we are focusing much on the industrial heating, and this by reducing the dependency on the fossil fuels, we could swiftly move on or swiftly transit from an greener energy. And there's a statistic for an Indian country, India. So more than 50% of the total energy consumption is taken up by this industrial energy. And here you can see that so industries such as the chemical industry, iron and steel industry, construction industry, paper and pulp industry. So likewise, many industries are contributing in this. So here you can see that the 42% of the imported oil is especially taken up only by the industrial sector. The remaining that goes to the power sector as well as to the transport sector. So here you can see a detailed uh, uh, details of the energy demand. So here, the 32% is of an industry thing. So out of which 74% is only heat energy. So out of this 45% is coal and 30% is natural gas and 15% oil and 9% renewables. So here, further, if you want to divide that this 74%, 30% is only a low temperature heating need that is of less than 150 degrees Celsius, such as processing like boiling, casting, cleaning, or the drying. Such process are requiring temperature which is less than 150 degrees Celsius. Next thing is of 150 to 400 that may be categorized as medium temperature heating. So that is primarily for distilling and melting, dyeing, and operations. So and there are some process which requires a very high temperature, especially the industries like a cement industry or iron and steel industries. They require a very huge thermal energy where the temperature is usually around 700 to that goes about 1000, 1500, 2000 degrees Celsius. So that is contributing about 48%. So here you can see that energy requirement and the temperature. So a major amount of the energy which lies in this region, that's less than 300 degrees Celsius, that could be easily met up with an renewable energy sectors. So that is the reason why we focus much on the uh, renewable energy sector for the low and medium temperature applications. Some of the industrial processes and the temperature requirements are listed here. So whereas in the dairy industry, so that we have many processes, so out of which the pressurization, sterilization, drying, concentration, they are in need of a temperature that have been listed here. Similarly, for the food processing industries or the tea drying industries, textile industries, paper, so we have many processes that require a temperature that is ranging from an 60 degree or 50 degree to around 100 degrees Celsius. Let's take an example of a milk processing unit. So where the raw milk has been received. So first it's been taken up to the chilling unit so that the temperature has been brought to about less than 5 degrees Celsius so that the lifespan of the milk can be extended. In case if you want to keep it for 2 or 3 hours, then the fresh milk can be or raw milk can be used. So in case by making it as by undergoing a chilling process, the life of the milk that could be extended up to 7 to 8 hours. So you would have seen that one that the milk packets that have been kept outside for 3 to 4 hours of time. So by the way, we are increasing the life of that milk. And again, that goes to the pasteurization process where the temperature is again been reduced to less than 4 degrees Celsius and it's been kept for a longer time. And again, from that, it's been taken up for the other process like in a cheese, buttercream, or for a drying for making a milk powder. Likewise, the products have been extracted from a milk processing. So it undergoes many a process. All these processes are in need of a thermal energy. So here you can see the process and the temperature requirements. So for example, for the cream separation, so we need a temperature which is in the range of 45 to 55 degrees Celsius, and where we are using a steam or a hot water for achieving this process. So in order to take it up or in order to separate this fat content and the pasteurization and ultra high temperature sterilization. So for each batch of milk, so all the equipment are to be cleaned with an hot water. So that is what we are calling as a sterilization. So it's been completely cleaned. So with a hot steam where we need a very huge temperature. And similarly, the other processes are also been mentioned for especially for making a milk powder. So we need to inject a high temperature air, which is ranging from 150 degree to 200 degrees Celsius. It's a cleaning in process. So that's nothing but an for each batch we need to clean it with a hot water or steam. So that's what mentioned here. And the temperature as well as the thermal energy requirements are being listed here. So you could clearly notice that the temperature and requirements for producing an 1,000 kg of these products. So in case if you want to reduce the carbon emission or for that we can say it's a decarbonization, so we need to adapt the renewable energies so that the uh, transition will be a very smoother or a swift one. So here the many of the industrial processes such as boiling, passing, so they require a temperature which is less than 300 degrees Celsius. That could be easily met with an solar process, solar thermal collectors. We have a wide range of thermal collectors which are available. Um, this utilization of the solar energy that is having a many advantages, like they are often uh, less dependency on the fossil fuels. So in the current situation also, you would have noticed that when the price of the crude oil that is varying, so depending upon the other scenarios, like a war between Russia and Ukraine, or uh, additional taxation by the USA government, or the reduced supply from Gulf countries. So these things are playing a vital role in the cost of the fossil fuels. So by utilizing a maximum amount of solar energy, we can have a lesser dependency on the fossil fuels. And again, the energy security can also be achieved. And by adapting or by using the solar energy, we can also achieve decarbonization or the low carbon energy, low carbon technologies. So when we are adapting, when we want to adapt this solar thermal energy, so here you can see a pictorial or illustrative one. So this industrial heating demand is completely a steady one. So there will be a very, very lower fluctuation. For example, for a chilling unit or so where we need to maintain a temperature of 4 to 5 degrees Celsius for at least for a period of 1 hour, 1.5 hours time. So in case if you are drying a uh, leather, so where we need to maintain a temperature of around 80 to 90 degrees Celsius. So there should not be any temperature flexibility. That means that should not go below 70 degree or 80 degree. So in case if there is a fluctuation in the temperature, there will be a quality issue. So by the way, almost all the industrial processes have a very lesser flexibility on the heating demands. So that's what mentioned here. So heating demand is like this. So the major drawback with the solar energy is of we usually get the thermal energy one day during the daytime. That is, especially during the noon time, we'll get a maximum amount of energy. So we cannot use the entire energy for this process. So and again during the other times, early morning or midnight, so we don't get an adequate amount of the thermal energy. So in that case, so we need to match the supply and demand. When we want to meet out the supply and demand. So obviously, we need to have a storage system for this. Yeah, question arises. So this may be placed for an electrical applications. So why we are focusing on this industrial thing? So again, that comes to the play. So industrial heat, so that is having a very limited demand flexibility, and moreover, so they are often completely decentralized one. So because of that reason, we are primarily focusing on this the industrial heating. And again, because of the pollution norms or the government policies, the most of the industries they are moving on to this fossil fuel dependence to the electrical systems, so that they can reduce their carbon emissions, so that their license can be extended and they can have a better carbon credits. The government has introduced a scheme that's of a tax scheme, that's a perform, achieve, and trade. So likewise, the government has introduced in many plans to reduce the carbon emissions from the industries. When we are integrating a solar energy for a process heating applications, so usually that will be like this. So conventional, either it may be a fossil fuel based one or maybe an electrical system based one. So and that's been used for the industrial process heating. And when we want to integrate a solar heat source, so in between we need to have a thermal energy storage so that the excess energy can be stored here. Again, the fluctuation can also be met with this one because the solar energy is purely based on the weather conditions. There will be a huge or a large amount of fluctuation. So in order to meet this fluctuation, we need to have a separate system as like we have a UPS at our home. So we need to have a thermal energy storage system in order to fulfill the fluctuation or to supply the additional heat requirements. And again, the one of the biggest challenges of integration of this solar energy as well as the conventional heating sources. We need to have a smart system that automatically switches the from a solar energy to the conventional so that there won't be any disturbance in the industrial process. So if there is any kind of a change or a disturbance, surely that will affect the quality because almost all the industries are run for 24 into 7. We cannot take a break. All right. So when we want to select a solar collector for this application, so we need to uh, focus on these parameters. They are often operation temperature of the collector, and for example, in case if you want to achieve a very lesser temperature that's around 70 degrees Celsius, the flat plate collector is sufficient. So when we want to go for a temperature which is around 70 degrees to 100 degrees Celsius, then we can go for an evaporative type of a collector. So in case if you want to achieve a very high temperature that may be around 150 degrees Celsius, then we need to go for a parabolic trough collector. So further, if you want to achieve a very high temperature that's within a 500 or 600 degrees, we have to go for a concentrated type of collector. Likewise, the operation temperature of the collector is to be focused here. And the next thing is of the heat transfer fluids. Which type of fluid that we are going to use it for transferring the heat, whether it's the air or a thermal fluids or maybe a water or a steam, which type of fluid we are going to use it for absorbing the heat. And then next thing is of the energy output standard certification. That means of, so as of now in our country, we don't have any proper certifications for thermal collectors. That's another drawback. Yes, sir. Sorry, sir. Are you able to hear me, sir? Hello. Manoj, sir, are you able to hear me, sir?
ఒట్టికొబ్బరి గిన్నె అన్న బెల్లం గడ్డ విరక్కోండి ఉండేదంట బెల్లం గడ్డ ఎండు ఖర్చూరాలు
Sorry, sir. Are you able to hear me?
Sir, yes, sir, yes, sir. I hope there are some disturbance from other participants here. Sorry, sir. I was
Okay,
thinking that you were talking with somebody else. Sorry, sir. Sorry. Please
okay,
go
okay,
ahead.
okay, sir. And the other thing is of the enough pressure resistance. So when for the process heating applications, usually there is a back pressure. So your system should have to withstand that pressure resistance. And again, the stagnation handling. For example, the heat which has been collected by the collector that has to be immediately taken away from the collector system so that the life can be extended. Otherwise, there will be a problem with the solar collector. So in what way we are going to remove the temperature. So that's what we are mentioning it as a stagnation handling and overheating prevention. And again, as I said earlier, the solar energy is a highly diluted form of energy, which requires a very huge or a large amount of floor space or a roof space. So when we want to install it on a roof, then the roof should be able to withstand the weight of the solar system. So all these things are to be considered here. And as you all aware of this solar collector system, it's a simple device, it's a simple heat exchanger where it collects the energy from the sun and it's been transferred to the uh, fluid, either it may be a water or a, oil or maybe air that's been taken away. That's what the simple solar thermal collector. And based on the achievable temperature, so we have already seen that for the temperature which is within 150 Celsius, it's of low temperature, and from 150 to 400, it's of medium, and it is above 300 or 400 is categorized as a high temperature. So now you can see a mapping between a temperature and the corresponding collectors. Again, based on the concentrating or a thing, so it may be categorized as a non-concentrating type, and again a concentrating, maybe a stationary type, and again a concentrating collector. So non-concentrating type collectors, so they will not change its position or a direction depending upon the solar movement. So that is what we are calling it as a non-concentrating type of collector. So primarily we are using a flat plate collectors, evaporative collectors. So and the flat plate collectors are almost outdated now. So most of the houses are being equipped with this evaporative type of collectors for the heating purpose or for producing in a hot water. Again, evaporative collectors, again, that may be of a direct flow ETC or a heat pipe ETC. So in case of direct flow ETC, the heat transferring fluid is been directly passed inside of this evaporative and thereby the heat is been extracted. Whereas in the indirect type or a heat pipe based one, so where we have a heat pipe, so that is inside, and again over the fluid is been passed over the condenser region of this heat pipe, so that the heat can be extracted from the system. And next to that one, here you can see there is a other categories. They are often compounded parabolic collector, parabolic dish, parabolic cross collectors. So where the position of the collectors are being changed with respect to the solar sun position. That may be either achieved by means of a manual way or a mechanical system, or maybe with an automated system. It's been possible to achieve. And depending upon the concentration ratio, we could achieve a very high temperature that may be around 150 to 300 or 360 Celsius can also be easily achieved. So when we want to go for a very high temperature, so you would have heard about it as a solar thermal power plants where the temperature produces more than 1,000 degrees Celsius. In that case, where we have a huge tower and almost we'll have a many number of reflectors that focusing on the topmost point of this tower, so that the receiver will have a maximum energy. That's for achieving a very high temperature, but it requires a very large space, so that could be installed only in a desert region. So here you can see the photographs of the collectors, flat plate collector, evaporated type of collectors, and parabolic collectors, again parabolic dish collectors, and the last one is of the solar tower. It requires a very large space when compared with the remaining collectors. So here you can see a simple water heating application. This is a solar collector, and it's been integrated with an process heating system. So where we have been provided with an additional or a secondary heater, so that the output temperature to the process will be of a constant. And we can say it's an equipped with a secondary air heater or secondary heating elements. And in this picture, you can see practically or a installed industry process heating up system. So where they have installed an evacuated tube type of a collector for producing a hot water, which is ranging from 50 degrees Celsius to 60 degrees Celsius. So they have installed a similar kind of a system in these three industries: Sona Koya steering system, and again Wheels India and Hydra heating systems. Actually, it is installed by our industrial partner. And the other type of an air heating system, they are primarily used in the food processing industries. So where the temperature requirement is less than 80 degrees Celsius, that could be easily made with a flat plate collector. They are of very, very old type of collectors. They have been installed almost 10 to 15 years back, not now. So right now they are using an evaporative type of collector for producing an hot air. The hot air can be used in the places like paint shops, or an automobile paint shop, or a large size of a casted parts welding shops. So where we can use it, and again for the rubber drying operations, and again the paper and pulp industries where we can use it, and the food processing industries. Apart from this, also we have other applications like chemical industries, cement industries, and again milk industries. So we have the uh, requirement of this hot air, which is ranging from 50 degrees Celsius to 110 or 120 degrees Celsius, which could be easily attainable with the help of an evaporative type of collector. When we want to achieve a very high temperature, so no other options, we need to go for an concentrators. So here you can see a reflector which concentrates the solar thermal energy which falls on this, and the reflector, sorry, the receiver. So where usually it's on a copper tube, and it's been surrounded by a glass tube. So it's a vacuum tube. By the way, we can achieve a very high temperature. So depending upon the temperature requirement, we could select a heat transferring fluid. And the photograph of the collectors are shown here. And in what way we can map the collectors with an applications that have been mentioned here. most of these low and medium temperature applications can be easily made with these type of collectors, flat evaporated evaporative with uh, uh, CPC that reflector at the bottom, and again the other type of parabolic collector, disc collectors that to be easily implemented. And here you can see the solar thermal technology and the temperature ranges. And again, they have been mapped with an industrial process. So for what applications we can use this that have been mentioned here. So when we have these many advantages or opportunities, why we are not able to adapt the solar thermal in these industries? That will be a big question mark here. So where it has many uh, challenges or barriers that needs to be addressed if you want to increase the solar thermal collector installation. First thing is of low volume demand. That means of um, when we want to achieve a very high temperature, we need to have a very large space. And again, initial investments will also be a very huge when compared with the conventional type of heating system. And again, the policy gap. That means of especially in India, we don't have a better policy or a subsidies for achieving a higher penetration of this higher penetration of the solar thermal collectors in the industries. But on the other side, for the PV systems, we have a very good policies. So because of that reason only, the India is right now in the third place in the worldwide. So we are the cheapest solar thermal energy, I mean solar PV energy producers in the world. So which costs about just one, uh, just about 2 to 2.5 rupees only. And the technical challenges. So again, I tell you that so we don't have a experts in the solar thermal system designers, and again the financial barriers. So the financial systems such as the banking or other sectors, they need to come forward for giving it, or they want to come forward to offer it in a better way. That's like in a subsidized way or uh, ESCO model. So we need to have such kind of a financial system for increasing the implementation. And again, the substandard components. So for most of the components that we are getting it, we don't have any standard systems or standard certifications for any of the solar thermal collectors. So it's been not yet mandated right now. So just last year only, uh, we, they have introduced a policy that all the components should certified with an ISO if you want to install it. And again, the government has introduced a policy like an perform, achieve, and trade scheme for increasing the utilization of an or in order to adapt a low carbon technologies. So it's yet to achieve its maximum benefits. And again, the energy service company model. That means um, most of the PV installers, they are adapting this technology. That's of the ESCO model. That means of so for the initial investment, the company, if they want to install a maybe 100 kilowatt in their industry or an organization, so that investment would be around a 50 lakhs. The electricity bill will be around 10 lakhs per month. So in that case, now they can go for this ESCO model. So initial investment, they have to pay around 10 lakhs rupees, and the remaining 40 lakhs will be taken up as a loan, and that will be easily paid with the help of this savings that we are achieving by installation of the solar thermal collector. I mean solar PV systems. So that is what we are calling it as an ESCO model. That means we need not to install or we need not to spend a 50 lakhs for the installation. So initial investment can be made. The remaining could be made with an bank, or the company will take care of that one as an EMI. And again, the domestic manufacturing. Again, I tell you that so the evaporative collectors are the when compared with the flatbed, they are the efficient ones, but still India is lacking a proper manufacturing facility for the evaporative collectors. So still we are getting it from China. We are purely depending on China. So for example, the tube that we are importing from China, which costs around 150 rupees, whereas when we start to manufacture it India, so Gujarat, there is a company, so they are manufacturing it. The manufacturing cost itself is around 250 rupees. So likewise, we don't have a support from the government for manufacturing these the thermal components. And again, the support system, in case if you are having any doubt on the systems or installation systems, then we cannot reach any expert quickly. So these are all the some of the barriers for the solar thermal installation in India. So till this, if you have any doubt, you can ask. So always we'll move on to the next part of this presentation, that's a thermal energy storage. Participants, if you have any doubt, you can ask that the contest that we have seen earlier. That's especially on the solar thermal collectors part. I could understand the difficulty of listening the last session and the last day. I could understand the difficulty, but still, if you have any doubt, you can ask on the solar thermal collectors part.
Yes, sir, it's going good, sir. No issue. We are all listening you.
Okay, okay, sir. I'll move.
Yes,
I'll be moving on to the next part. That's the thermal energy storage part.
yes, sir. Yes, sir.
Um, So as I said earlier, the when we want to increase the adaptability of this solar energy, so we need to have a properly designed thermal energy storage system so that the excessive energy can be stored again, or else the flexibility, I mean the fluctuation in load can be easily met with this. By the way, we can have a increased installation of the solar thermal collectors again. So uh, storage systems are primarily used to meet the supply and demand concepts. So that demand may be of a daily basis or a hourly basis or maybe a weekly or sometimes that may be a seasonal thing, especially in the Europe and kind of a country. So where we have a seasonal storage system. So you would have heard about the word that's of a residential heating. So especially in the colder regions, they use an room heaters. So if in the Europe countries for about an 3 to 4 months period of time, so they may have a very higher snowfalls. That means the temperature will be around that usually falls below 5 degrees Celsius. So in that region, they need to have a continuous heating to their houses. So in that case, they are adapting a district heating kind of system. That means similar to that of our electricity, they have a centralized heating system. Only the hot energy is being circulated to the each of the houses. Else they can go for an solar thermal collectors again. Otherwise, they can go for an seasonal based thermal energy storage systems at the underground. That could be used for getting an heat energy or maybe cold energy depending upon their requirement. And when we want to use a thermal energy system, so we need to pay clear attention to the parameters like storage duration. Uh, how much hour we need to store, whether is it for a 1 hour or 2 hour or for 6 hours, or maybe daily or weekly, or that we need to decide clearly. And again, the economic viability. So here it plays a very important role. That means often the cost of the uh, cost uh, that varies depending upon the medium or a technology that we choose for the thermal energy storage. And again, the supply and utilization of the temperature requirements. So whether what kind of a supply that we need, whether we want to have a hot air or a hot steam or a hot water, what kind of supply that we need. And again, the temperature requirements, whether are we in need of 50 degrees Celsius or 60 degrees Celsius, whether is there any uh, uh, possibility to have a flexibility. That means a change in the temperature at 55 or 50, 60, or do we have to supply a short temperature to this process? Likewise, we need to have some kind of a requirements about the temperature and the supply characteristics. And again, the storage capacity. That means that here we are not talking about the temperature, that's the quantity of the heat energy that we need to supply. So accordingly, we have to select a storage system. And again, the heat loss, obviously, when we want to store it for a longer duration or for when we want to transfer to the other system, usually there will be some kind of a heat losses that may happen that we need to take care. So how much energy that could be lost, and that should also be taken into account when we are designing a thermal energy system. And again, how much space we are having it in case when we are using a sensible heat storage medium, we need a very huge space. In case we are using a latent heat storage system or a thermochemical system, so the space requirement will be of a lesser than the sensible heat storage. So, likewise, we can to focus on these parameters. Actually, these contents have been taken from an Europe kind of presentations. So where they are spending a huge amount for the district heating purposes when compared with the industry heating. So they are spending a huge amount for the residential heating. Okay, again, this is the basic kind of a thing. So basically, the thermal energy storage system can be classified into three methods. They are often sensible, latent, and again chemical or thermochemical methods. So again, the sensible may be often solid, liquid, or other things. This is a fundamental. Yeah. Nowadays, the different materials are being explored or demonstrated by this many researchers. Cryogenic heat storage, latent heat storage, sensible heat storage, thermochemical storage, and we are using some combination of the sensible heat storage and latent heat storage system based on the demand. Based on the demand, we can have a short-term or long-term kind of a system. I think the sensible heat storage principles are been shown here. So that means then during the absorption or charging or discharging period, that will not undergo any change in its phase. So only you can see a sharp or slight change in the temperature by the way it takes up the heat or it discharges the heat. So the depending based on the characteristics or based on the type. So it may be of a liquid, solid, or maybe a dual kind of a system that may be used here. Sensible heat storage and latent heat. So that usually undergoes some change of phase. So either that may be a change of phase from solid to solid or solid to gas, solid to liquid or liquid to gas. So in most of the cases, we prefer the solid to solid or solid to liquid. So when we go for a solid to gas or liquid to gas, the gas is a very less denser one. So that will occupy a very large volume. So because of that reason, we don't prefer the solid to gas. And again, the leakage will also be a bigger problem when we are choosing a solid to gas or liquid to gas kind of a system. So here you can see that when compared with the sensible heat storage medium, so the latent heat storage medium are capable to absorb a very huge amount of heat. That means the energy density is much higher than the sensible heat storage. That means initially that takes up the heat from a sensible way. That's of a increasing temperature when it is attaining a the change of its phase temperature, then that takes up the heat, and again that changes its phase. So by the way, it absorbs a huge amount of energy, and during the discharging cycle also that reverses. So the volume requirement of the latent heat storage is lesser than the sensible heat storage, and we have a wide range of materials for this latent heat storage. So that may be of an organic, inorganic, or eutectic. So we have a huge number of materials, more than 100 or 1,000 kind of materials are available for exploring it. But still, the problem is that so most of the materials are not explored. And especially in the carbonic truss collectors or maybe in the concentrated of collectors, where we're using a molten salts. So usually they are in the solid form. So when it's been raised to the temperature of 250 to 300 degrees Celsius, where it changes its state from a solid to liquid. So that has been used for collecting heat. So that has been usually adapted for a temperature range from a 250 to 600 degrees Celsius. That could be easily used, and that will be in the form of a liquid, so that the energy can be easily transferred to the processor. So here you can see that there is a system. So it's a two-tank storage system. That means a low temperature fluid and again the high temperature fluid. The low temperature fluid where the fluid is being taken again that's been sent to the parabolic reflector where it collects the heat and again that reaches temperature of 515 and that goes to the hot storage tank and from there it's been taken up to the process. So here it is a steam generator is being shown. Steam generator where the steam is being produced that goes to the power plant again that goes. So it's a kind of a power plant. So So here you can see there is a difference between this and this. So here we are supplying only the thermal energy to this system. That's how we are calling that the indirect system. That means of where we have a two type of fluids. So here we have a separate heat transfer fluid and again here we have a separate heat transfer fluid. So by the way, the molten solid that remains only in this stage. So that the designing will be of a simpler than this one and the life will also be higher than the direct kind of system. And when we go for an concentrated type of collectors, so most of the cases we are adapting a two tank storage system. That means for a colder fluid we have a separate tank, and for the hot fluid we have a separate tank. So this is what we are calling it as an salt, or we can say it's a solar salt or a molten salt. So usually in the form of a solid. So when it has been raised to the temperature of 250 C, above 250 degrees Celsius, so that changes its phase from a solid to liquid. And again, when it reaches about 600 or 650 degrees Celsius, that starts to disintegrate. That's what the major problem with a molten salt that cannot be used for a very high temperature, such as a 700 or some degrees Celsius. Yeah. So here you can see the type of a storage system and the temperature. They have been mapped together. So when we want to store, when we want to achieve a very high temperature, so no other options. We have to go for a chemical storage method, chemical storage in thermochemical methods, or maybe a hydrogen production that could be used. So in case when we want to go for a very low temperature that's less than 100 or means to 500 degrees Celsius, we have a many options such as molten salts or composite PCMs. Again, the sensible heat storage mediums are available. So here you can see a large blue color box that indicates a sensible heat storage medium. So mostly in the form of a solid state. So here your question may arise, so what kind of a material that can be used as a sensible heat storage? So commercially we are using an concrete, steel, and water, rock, and sand is nowadays sand is also being used as one of the solid state sensible heat storage medium. Underground thermal storage systems. So likewise, we have a very large number of options are available when we want to achieve a very low temperature that's ranging from 150 degrees, 500 less than 500 degrees Celsius. Even for sub-zero also we have options like an ice and again other systems are available. When we want to use for an industrial heating applications, so these are the things. So for low temperature applications, uh, tank-based thermal energy storage, salt hydrates can be used. And when we want to go for a medium temperature applications, we can use a composite PCM. And for achieving a very high temperature, where you can go for a chemical looping, or that's nothing but a thermochemical method. And for all these ranges, we can use a solid state. That's nothing but a sensible heat storage medium can be used. So we have to select a suitable material which could withstand or which could transfer the temperature. Okay. First thing is often sensible heat storage medium. So most of the places where they are using in water as one of the sensible heat storage medium where it's possible to achieve a temperature which is less than 100 degrees Celsius. So it's a highly matured kind of a technology. So it's been commercialized widely. And the next thing is often PCM or phase change materials. So they have not attained its complete commercial stage. That means still we are in the lab scale model or in a pilot scale study only. So it has not attained its commercial stage. But there are some companies which are doing the commercial installation, but they are not so popular as like in a sensitive heat storage system. And when it comes to the last stage, that's for the thermochemical method. For example, the best known thing is often the hydrogen production. So when we want to produce a hydrogen, that's nothing but electrolysis process, where we are able to supply a temperature which is above 500 degrees Celsius. Easily we can separate or we can produce a hydrogen gas that could be stored in a solid carrier. That's nothing but a hydrogenation process, where that will emit a huge amount of energy that could be stored in a medium again. So further, when we want to achieve that, or when we want to extract hydrogen, again we need to supply the uh, thermal energy. Hydrogenation, dehydrogenation process that will take up. So for the required temperature can be easily supplied with this uh, concentrated solar power plant. When we want to select a suitable technology, so we have to consider these parameters. First thing is often, let us take a sensible heat storage medium. Sensible heat storage materials are highly cheaper. That means the materials like a water or sand or rock, steel, concrete, they are very cheaper when compared with the other kind of a materials such as PCM or other materials. So that's a major advantage of the um, materials when compared with the other type of materials. So next thing is of the lifetime. Whenever that goes to change of its phases, there may be some deterioration on its characteristics, so that cannot last for a longer duration, maybe 10,000 or 15,000 cycles. So that means often for every day that may undergo one cycle. So that will not be more than a 10 to 15 years of time. So again, we have to make a huge investment for this one. So uh, when it comes to a sensitive heat storage medium, the lifetime is much higher. That means the rock or a concrete that will not deteriorate much when compared with the PCM. And again, the round trip efficiency, that means the charging and discharging efficiency. So sensible heat storage mediums are having a very high uh, charging and discharging efficiency. It's more than a 70 to 80 degrees Celsius. So here it's been mentioned as 90 to 95. So that depends upon the material that we are using it. And again, the materials which could be used are often molten salt, silicon, concrete, refractory brick. So these materials are most commonly used as a sensible heat storage medium. And the commonly used heat transfer fluids are of a water, a steam, air, thermal oil, supercritical CO2. For example, in case if you want to use water as um, a heat transfer fluid, so in that case we cannot use a refractory bricks or a silicon or a molten salt as a storage medium. So where we have to use a rock as a storage, storage medium. So when we are using an air as a heat transfer fluid, there we can easily use an refractory bricks or we can say it's a thermal battery that can be used. And the drawback or a downside of the sensible heat storage is of its energy density. When compared with the latent heat storage medium, the energy density of the sensible heat storage is very less. So that's the major drawback of this one. Let us see some of the commercial thermal energy storage installations. Here you can see Rondo, that's the company name. They have produced an heat batteries, or we can say it's a thermal batteries. So here, as a battery in the sense, they are mentioning it in terms of an energy storage. So here, the heat, I mean, the thermal electricity has been used for charging the heat batteries. That means that the thermal heat and electricity has been converted into thermal energy, and that thermal energy has been stored in the refractory bricks. They are just like a brick kind of an arrangement. So the temperature, the energy is stored in form of temperature in these bricks. So whenever there is a requirement, the air is being circulated through the system. So where it gets or where it gained the heat, that heat has been taken for the further process. So this is the way it works. because whenever there is a fluctuation in the electricity supply, that means during the daytime we'll get a higher amount of electricity that could be stored for the later process. So here you can see some of the renewable energy systems, wind energy, and again the solar, and finally the power plant kind of thing from the grid. So that could be easily stored. Any kind of electricity that could be used for producing the heat energy, and that could be stored here. So here you can see the photograph of the thermal battery. So when the thermal battery at its fullest capacity or at in highly charged condition. So you can see that the red color indicates that it is at the charged condition. So when we are circulating in air through this system, that will immediately heat it up, and again the hot air can be used for the process. And it's at the normal state. Uh, just there like refractory rock, sorry, refractory bricks that's made up of a kind of a clay. They are in the different shapes. So here you can see that so their gaps are provided in order to circulate the air in order to absorb the energy from the bricks. The company which is called as a Rondo, they are introduced this kind of a technology, and they have installed commercially. They have installed in a factory. Yeah, that's it. The company which is Rondo and the CM Cement Group, so SEG, so they combinedly installed their large thermal energy, sorry, thermal energy storage system in at Thailand. So for the cement industry, so where the temperature requirement is more than 800 degrees Celsius. So usually they require temperature which is 1,100 degrees Celsius for the calcination process. So this temperature can be easily met with this, that could be easily supplied with this thermal energy storage system. And electricity is being converted into heat energy. That heat is being stored in the grid. So whenever there is a requirement of the heat energy, that's been taken with the help of the hot air. So continues that goes on. So this is all the advantages. So it charges for the 4 to 8 hours, and again that's been able to supply for another 8 hours. So that means the fluctuation, the electricity, or the other things that have been not affecting the production of this industry. And again, so here we are not using only the electrical energy. So that means we are completely eliminating the dependency of the fossil fuels. The next thermal energy storage system that's been installed in a brewery industry, which is located in Italy. So where they are able to produce a hot water for its brewery operations. So that's been produced by means of the parabolic trough collectors. And where they are using an water as a sensible heat storage medium, and that can use for the processor. And whenever there is a requirement of the steam, that is also been excited on this. And next thing is an food processing industry, which is located in Finland. So again, here they are using an electricity for charging the thermal energy storage, which is they are having a capacity of 10 megawatt, and which is capable of delivering a 180 degrees Celsius at the temperature, I mean, at the pressure of 16.9 bar. And here they have made an economic study that performs, which is capable of replacing an 264,000 liters of fuel per year. By the way, they are reducing, they are decarbonating the system, and the company which has installed the thermal energy storage of Elstar, and that's the company in a Bournemouth in France. So they have installed a system like this. So where they are using an yeah, solar thermal collectors for heating the fluid, and that's been stored in a storage tank, and that will be taken up for the processes, depending upon the requirements. So the temperature requirements that may be of a different that's been used. Again, which results in the reduction of a 2,000 tons CO2 per year. And the thermal energy storage, which can be easily met with the help of the fossil, uh, renewable energy systems. So here, for what are the applications we can use it? So first thing is for the cogeneration. That means whenever there is an requirement of the power as well as the process. So where we can say it's a cogeneration process. So where you can easily adapt this thermal energy storage system. That means let's take an example of a steel industry where steel has been melted at a temperature of 1800 degrees Celsius. So during the solidification process that emits that much amount of that means almost 1000 degrees Celsius has been emitted to the ambient conditions. That could be easily collected for the further industrial processes. Mm. That could be stored in a thermal energy storage system, and again that could be used for the further process. That means the process and the power generation, if you are able to combine it, that's a cogeneration process, that will be more efficient than the simple systems. And uh, the fuel for the boilers, that means those systems can be used for the power generation options also produced in the steam and for the process operation. So like this, we have a different kind of applications in the industries such as chemical industry or refiners we need, and again the product for producing the fast products and food and beverages, iron and steel industries for the especially for the plastic industries we need a huge amount of heat for melting the plastic material. Likewise, um, this thermal energy can be easily met with the that could be supported with this thermal energy storage system. So here you can see a simple power plant which is capable of producing some electricity. So here they have installed a parabolic trough collector and coupled with a hot and cold storage. That's a two-tank storage system. And from there, the electricity has been produced and that's been sent to the grid. So similarly, here you can see a CSP.
Sir, cake.
Hello?
Sorry.
Yes, sir? Am I audible, sir?
Yes, sir. Sorry, sir. Sorry for this.
Okay. It's a concentrated solar power plant where the thermal energy is being collected or it's received at this point, and where when we are circuiting the heat transfer fluid to this tower so that we can uh, uh, receive or collect the heat from the tower, and that's been stored in the hot storage. So whenever there is a requirement, that's been taken up for the power production, and that is been sent to the grid. So likewise, it could be used. So where that the requirement of the storage systems are very, very essential because the solar energy is not available throughout the day, or they are changing with respect to the climatic conditions. They have been changing continuously. So that could be easily fulfilled with the help of this storage tank or storage systems. So here you can see the thermal energy storage commercial readiness level for the industrial applications. So in the research articles, you could see a huge number of papers, especially in the PGM materials. But when it comes to the commercial applications, they still not attained a commercial level. So here you can see that one. Sensible heat mediums. So here we can see that solid state and molten state materials, they have attained a commercial level. And the latent heat storage medium, so the PGM materials, like a metal alloys or composite PGM materials, they are in the level of a pilot type or they are in the research level only. So, but they have been installed in a huge level, but still they are under study for the further commercialization of the one. And at the thermochemical thing, that's like absorption or absorption or the chemical reactions or the hydrogen production, whatever it may be. So they are still in the level of research. They have not even crossed that laboratory. So they are still in the laboratory level studies. So it is clearly seen from this figure that so only the sensible heat storage mediums have attained an full commercial level implementation. TS, industrial heating applications by temperature. Steam generation recovery. Uh, So here you can see that industrial processes and the corresponding temperatures. So below which you can see the uh, possible materials that could be used here. So for when the temperature is lying in the range of 600 degrees Celsius, easily we can use a molten salt. So when it is crossing a temperature of 600 degrees Celsius, we cannot use a molten salt here. So where the solid state materials that can be easily used up to 1000 or 1200 degrees Celsius. So again, when we want to use the temperature in the range of 600 to 900 or 1000 degrees Celsius, where we can use an phase change materials and the other kind of materials that yet to be explored now. So the some of the industrial processes are listed here: the steam generation or a heating process or process fluid heating and curing, pasteurization or melting, calcination. So some of the processes are listed here. So depending upon the temperature requirements, we can have a selection of the suitable or appropriate thermal and storage medium. So here you can see some of the companies or industries which are focusing on thermal energy storage. So from the USA, you can see there are some known players in the market. They are of Antora, so they are focusing Antora and Rondo. Both of these companies are focusing only on the sensible heat storage, that too solid state heat storage. So one company is focusing on stand batteries and the other company is focusing on a thermal battery, which works with their bricks. Similarly, the other companies like Ecogen, Malta, so they are also working on the sensible heat storage kind of systems. And the next company, which is often MGS Thermal. So slightly they are using an patching material kind of patching materials for its thermal energy storage. So, but especially in our country, we don't have a completely renowned thermal energy storage installation or maybe the manufacturer who is focusing exclusively on the thermal energy storage system. So there are some companies which does this option as one of their business, not as of their sole business. Because of that reason only, we are not able to attain a complete commercial stage as like the other companies that they do now. And so here you can see that the as of now we have seen a different kind of a thermal energy storage systems. So that works with the energy that have been usually produced and they have been stored and that have been used for the further operation. So the next thing is of the waste heat recovery system. That means of there are some heat. So whenever we are able to adapt a technology which is capable of recovering the heat from the process, so that will be more than the energy that's been produced. So here, the 20 to 50% of the industrial input energy is lost complete as an waste heat in the form of a hot flue gas, a cooling water, or the surface heat from the equipment. That's the last. So if you are able to provide a well-designed waste heat recovery system, and if you are having a suitable energy storage system for storing this recovered heat, that could be an economical way of storing or economical way of spending the energy. And there is a company, they have implemented this waste heat recovery system in a steel industry. So here you can see that so there they have a electric arc furnace industry, which is losing it or which is capable of producing temperature which is more than 1200 degrees Celsius, and most of these energies have been lost when it's been used for a solidification process. So in that case, they have decided to recover that heat within a suitable waste heat recovery system, and that's been stored in a dual media packed bed. That means of the rock carbon usually kept in the storage tank, and the dual media in the sense that so one medium is been for transferring the heat or charging or discharging. The another one is been the stationary level. That means you think of a combination of a water and or water, maybe a thermal fluid, or maybe rock. So in that case, the rock is been kept in a storage tank, and where the thermal fluid is been circulated inside of the packed bed, so that takes up the heat from the recovery system, and that's been stored in the storage tank. So that way, it's been called as a dual media packed bed, where the energy has been taken from the steel slag, and which is capable of storing a temperature which is above 700 degrees Celsius, and the recovery efficiency is more than 85%. And the other things, if you're able to design it, or if you're able to deploy it in a proper manner, so we could achieve this cost effectiveness and the temperature, I mean, efficiency. So, and by the way, we can have an circular economy. All these advantages can be met. So they have successfully implemented this. So here you can see that schematic of this operation. So where they have a system as like this. So it's a two tank storage system. That means one tank is in operation at a time. So one tank is in charging condition, the another tank is in the discharging condition. So once it's been discharged completely, the process is being transferred to the charging tank. So that the process is continuous. That means that we are able to recover the heat whatever is possible from the system. Everything has been stored and it's been used for the later purpose. Some of the applications are mentioned here. That for the preheating of the scrap, or for producing a steam, and for producing a hot air. Likewise, they are using it for the many of their process heating applications. So there they have used a thing that's a double tank operation. So one tank charges, the other one discharges. Likewise, that goes on. So and they have achieved a efficiency which is ranging from 65 to 70%, and the temperature which is in the range of 700 degrees Celsius. And additional thing, that's a chemical energy storage. So still it is in the research level only. That's of the hydrogen as a thermal energy storage medium. So why do we want to focus on the hydrogen? Because the reason is that hydrogen is 3 times energy denser than the petrol. So that means the energy density is very high. And again, the other thing is that the byproduct. So it will not emit any kind of a I mean, it will not emit a carbon dioxide. That means the byproduct is only of a water. So it will not be harmful to the environment. So because of that reason, in case we want to go for a greener or a cleaner energy or decarbonization stages, so the best option is often hydrogen. So if you are able to produce a hydrogen with the available thermal energy, and if you're able to use a hydrogen for your applications, then that will be the maximum possible achievement by a thermal energy storage system. So here, the energy that is required for separating or for the induced the electrolysis process, and that could be used. And further, the hydrogen can be used to produce a heat that by completely combustion, either as a heat energy or the electricity. So if you are able to supply it through a fuel cell, directly we can produce an heat energy. And other things I will mention here, and it is the reverse ESM. So there are many methods are available, so that I will listed here. And the production and color coding system. So here you can see different colors of the hydrogen. So don't think that the hydrogen is in the different colors. So we are using a different color coding in order to identify its source and the possibilities. For example, if it is of green hydrogen, means it's been completely produced by means of an electrolysis process, and the electricity that you're using it is from a renewable energy. Purely, it's a green energy. That's what the hydrogen. And again, the gray hydrogen, the sense that so where we are producing an energy, splitting in natural gas, and it's been released to the atmosphere. Again, we are releasing the hydrogen, I mean carbon dioxide to the ambient. And if it is of blue hydrogen, means we are been capturing the high CO2. That's the difference. And the brown, brown and black that have been produced from a coal or a lignite material. And if it is of pink hydrogen, in the sense that if you are using a nuclear energy for producing hydrogen, that's called as a pink. Okay, that's all. Okay, thank you for patiently listening my session. In case you have any doubt, you can ask now.
Vijayan, sir, it's a nice presentation.
Sir, thank you, sir.
Nice presentation, sir. Thank you for your wonderful presentation. I hope our participants have enjoyed the session. So now the forum is open for the questions. If participants are having any questions, you can let us know.
If you have any questions regarding the implementation, so actually, solar thermal energy is our focus, and we are working on it. And we are working on a solar thermal collectors as well as a thermal energy storage system.
I think the participants are clear about the presentation. I hope so. Anyhow, it's a long session, sir. We are really happy about you for your patient presentation.
Okay, thank you so much. Thank you so much for giving me this opportunity, sir.
It's a pleasure, sir. It's a pleasure to have you here. And on behalf of the Department of Mechanical Engineering, Adishangra University, and on behalf of all our participants, we thank you once again, sir, for giving this wonderful presentation during this evening time. And definitely we will again collaborate with you in future. Also, sir. Thank you so much for.
Thank you so much. So I would like to express my thanks to all the participants for patiently listening to my session. Thank you to everyone. So if you have any doubts or if you want to collaborate or if you want to work with us, you can contact me at any time. We'll share our contact details with the coordinators. You may get it from them. Thank you, sir.
Thank you, sir. Thank you so much. Nice, sir.